Okay, so we will discuss today this amortized analysis. But before that, as we were discussing this knapsack fractional knapsack problem. Okay, fractional knapsack problem, and we have seen that if we fractional knapsack problem, and if we are going by this VI by WI ratio, okay, VI by WI ratio, then we are getting this optimal behavior. Okay, VI by WI ratio, and this knapsack problem. If we are thinking this knapsack problem very fundamentally, then we are seeing that okay, we are having a bag, we are having a knapsack that is having a limited capacity. So we can think of say this knapsack as a scarce resource. Okay, so we are limited by that amount knapsack capacity. That could be a budget also. Say we are limited by a budget, right? And there are several guys who are having different productivities and salaries that might be resembling this VI and WI. Okay, so how we can hire uh, all the all the desired candidates. Okay, so so we generally start with the knapsack problem with that example that a thief is coming inside the room, but actually it is much more fundamental. Okay, knapsack problem. So that whatever I have right now said is that whenever we are thinking about some scarce resource and some supplies are there with productivities and maybe salaries. Okay, so that means that are resembling this valuation and weight, then we can think of that problem is nothing but the knapsack problem. Okay, anyway, so this fractional knapsack, we have seen that okay, if I am going by this ratio, ascending or this highest one we have to pick up, so this is descending order of that we have to go by, and then the highest one, and then the next highest one, and the next highest one we have to pick up like this until the knapsack capacity is exhausted. And we have seen that it will be filling the knapsack exactly as well, because we can take fractional capacity, right? Or we can take fractional amount. And if we have to prove that okay, this is this approach, that means if we are going by this VI by WI ratio in a descending order, so that will be leading to the optimal solution. So here the proof is again will be relying on this greedy stays ahead property. Greedy greedy stays ahead. So that we have already seen a proof like this. Okay. So in this case, greedy stays ahead. What we are thinking that okay, let us think that my algorithm, my greedy algorithm. So this is my algorithm, and say any other algorithm. So that is running parallelly on the same data. Okay, the same data we are running parallelly, M and A, and up till some point, up till this ith iteration, they have selected the same thing. They have selected the same thing. Okay, and they have filled the knapsack by selecting the same thing. Okay, and then in I plus 1th iteration, what will be happening? I plus 1th iteration. So in I plus 1th iteration, if we are looking at this greedy algorithm, that means VI by WI ratio, what we are seeing that for filling up the remaining capacities, say this is the remaining capacity. For filling up the remaining capacity, So we are taking the next vi by wi ratio, right, which is the maximum. So that will be my algorithm, okay, my greedy algorithm, fractional knapsack algorithm that we are discussing. That will be taking the next best available vi by wi, okay. And now you see if this algorithm is exactly thinking like greedy, then it is okay. Otherwise, if this algorithm thinking any other way, then that will not be taking the next best available. It will be taking other one. So it cannot be the optimal one. It will be a suboptimal one. Okay. So that is the greedy construction that we are having is proving really good. Okay. So always we are taking that up till this point. Everything is same, and then what will be happening in the next I plus 1 iteration. Okay. So that is the idea with which we can prove that this fractional knapsack will be leading to the optimal solution. Okay. Okay. So next, what we'll be doing, okay, before discussing this amortized analysis, and this amortized analysis, the reference will be, as usual, is this CLRS book. Okay. And maybe in that week, say, I guess 21st to 27th. Okay. 21st to 27th, we are having a midterm week. And second assessment, that is the midterm, right? So we'll be taking the exam in this 21 to 27th. Okay. And as this will be a common exam for all the three groups. Okay. All the three groups, one common exam will be taken. Okay. That means at the same time the exam will be happening. So you will be logging to, sorry, am I audible? Mhm. Okay, okay. So three groups will be giving the exam at the same time with the same question set, right? So you will be logging to my Moodle account. Other group will be logging to their respective teacher's Moodle account, and the question will be delivered at that time. So you consult your peer groups and you fix up a date, okay, in between this 21st to 27th, and tell me which date will be better. And as I think we cannot take in the, if say if we stay at the same time, all three groups having the class at the same time, then at that time in the class hour we can take. Otherwise, if fix up a time that might be, I think, 5:30, something like that. Okay. But preferably you check the routine that all three groups will be having at the same time. Say it might not be 3 p.m. In the original routine, it might be some other. Okay. So you check which timing will be better, and then at that time we can take, but we cannot go beyond 27th. Okay. So that is the mandatory issue, 21st to 27th. And all the classes which will be discussed in this week, that will be covering the syllabus, right? Okay. So you fix up the date accordingly. Okay. Now sorry, sorry. Okay. You inform me. Different. That I have already said. You'll be joining to my Moodle. Respective other groups will be joining to other teachers Moodle account. Okay. And accordingly, before 5 minutes of the exam, question might be distributed in the Moodle account, and then you download and write the way you have given the first one. Can, for the timing, this is this may be changed, but this could be the organization. But you fix up the date. Hmm. Okay, so now we are dealing with this amortized analysis. So, what is this amortized analysis? So, this for a sequence of n operations, what we find so far, what we find is the worst case running time. Okay, but uh, but for amortized analysis, what we are doing is for a sequence of n operations, we find the worst case running time with the detailing and find the average worst case performance. That means worst case per operation. That will be the amortized cost. Okay. So take an example of n sequence of operation. When this n sequence of operations will be coming in many algorithms, it comes. Say for example, say we are sequentially pushing and popping n number of items into the stack. Okay. Sorry, we are pushing and popping n number of times into the stack, pushing and popping. So this is the stack we are having. So first one operation is taken place. This is operation one. Then operation two, another say push operation, another push operation. Then maybe another pop operation happens. So in that case, the the stack configuration will be like this. So we are deleting the elements from top, that is the stack property. So this is how many sequence of operations here already happened. One, two, three, and then another pop. Okay. So this is push, and then we are having another push. Okay. Then another push, and then pop. Okay. So these operations so far happen. So this is called the sequence of n operations happening. Sequence of n operations. So to understand the idea of this amortized time complexity, let us take one more example, and in this case, a for loop is coming. Okay. So we can think of the for loop as a sequence of in operations as well, right? So let us take this code fragment here. Let's take this code fragment here, what we are having. So here what we are doing is for I equals to 1 to n, something is happening inside this. And within this for loop, there is a while loop happening. Okay. And some statements within the while loop will be operating, right? So what will be the conventional worst case analysis for this hypothetical assumption? Say a few times while loop executes in number of times, and for rest of the iterations while loop executes constant number of times. So you are setting the while loop condition in such a manner that based on this sequence of n operations, this while loop will be executing, say, uh, a constant number of time. Okay. Sorry, this constant number of time, or this it might be executed in number of times as well, right? So we can say it here is that this while I equals to 1 or 2, then while loop will be executed in number of times. Otherwise, a single time, something like that, right? So in this case, what will be the worst case time complexity that you will be judging for this code fragment? Okay. So the conventional method that we discuss, that we have discussed, so that conventional method takes what kind of approach? We will be seeing that, okay, this while loop is executing at the worst case order of n time, and then for I equals to 1 to n, I equals to 1 to n, for each of the execution while loop will be executed order of 1 time, and then the time complexity will be order of n square. So this could be this could be the idea that we can employ whatever we have learned so far, right? Whatever we have learned so far. But this is there might be a problem, but or you can think of this. Although this analysis is right, but this analysis may not be tight. Okay. So this may be right, but may not be tight. So that is the case. It may be right, but may not be tight. So let us take a detailed view of this. So if we analyze that way, it may not be a tight estimate. So why this will not? As the while loop is getting executed few times, few times executed a few times, we have to write for a proper correct English, a few times with order of n, right? So what we are observing here is that while loop inside the for loop, while loop is very often uh, uh, a few times while loop is being executed order of n time. Other than that, very often it is executing, or it is getting executed this order of 1 time. Okay. Order of 1 time. So this is the observation. This observation is very important. This observation is leading to the fact that, okay, whatever uh, analysis we are doing in the worst case, that may not be tight. So we can think of that the outer for loop happening sequentially. So for a sequential n operation, so the for loop for each I equals to 1 to n, I equals to 1 to n, that means we can think of that this is a sequence of n operations going on. And for a sequence of n operations, something will be happening inside the while loop. So now, as we have argued that in the first slide, what is this amortized analysis? So we have seen that we are doing some kind of detail analysis, or we are seeing that we are doing some kind of detailing. So if we are now detailing this, if we are detailing here, in each execution what is happening, if we are having a go with that, then we are observing that the first operation while loop executes say order of 1 time. Say the second iteration, the while loop say being executed order of 1 time. Third time it is getting executed order of n time. Fourth, fifth, order of 1 time, fifth order of n time, and rest of the cases order of 1 time. So if this is the case, then how can we analyze the overall time complexity? So Tn, if we are doing, so this will be first operation cost, then the second operation cost, then the third operation cost, plus the fourth operation cost, fifth operation, and so on, right? So that is the way we have to do. And we are seeing that n minus 2 times order of 1 time it is taking. And 2 times it is taking order of n time. So now this n minus 2 times order of 1, that will be order of n. That will be order of n. Plus 2 times order of n. 2 will be subsumed inside order of n. So it will be again order of n. So then it will be order of n plus order of n. So in that case it will be this order of n, right? So you see, this is a much more tight analysis we are doing, much more tight analysis. So we have already got the philosophy. Now this per operation average cost, we have to find out per operation average cost. So we are having a sequence of n operations, sequence of n operations, okay? And sequence of n operations is resulting Tn equal to order of n time. So what will be per operation cost? So that means the average cost. So this will be maybe this T prime n, that will be equals to order of n plus this divided by n, as we are finding out the per operation cost. That is the average cost. So this will be order of 1, right? So so we show here is that the average cost of an operation is small. Average cost of an operation is small. If we average over a sequence of operations, even though, this is very important line, even though a single operation within the sequence might be expensive, as we have seen that two times these for loops, while loop taking order of 1 time. So even if a few of the operations might be expensive, but if we take the average, that expensive behavior will be distributed throughout. This could be thought of as a mobile credit. Whenever you are charging the mobile phone, you are giving a huge amount of credit there, and then whenever next time you are calling, you are all those callings, for that you don't have to recharge again. So whatever credit you have stored, from there it will be debited. That means that cost is getting distributed throughout. Okay, that cost is getting distributed throughout, and you can think of that as if uh, after recharging every call, as if is coming to you free, as a free calling. Okay, so even if some of the operations are expensive, if we are distributing, as a thought experiment, we can think of that all these operations are being distributed throughout, making each operation average cost small. Okay, so that is the main idea of this amortized analysis. So far what we have got is for this amortized analysis. In a nutshell, if we are thinking that, okay, this amortized analysis is what, then we will be telling we are doing some kind of detailing in the analysis. And what is the utility of having that detailing? The utility of having that detailing is that the average cost per operation will be small, right? So that means even if few operations are getting expensive, we can distribute that cost throughout. That is the sole idea of this amortized analysis. Okay. So in amortized analysis, we do some kind of detailing and then we take average. And the beauty is that even if we are taking average, there is no probability involved. No probability involved. As we have seen here, right? We are getting the total and then we are dividing by the per operations. That is our averaging principle here. And that is the, we are not going to have any kind of distributional assumption on the data. That we do in average case analysis in algorithms, okay? Average case analysis. So this is not the average case analysis, right? Okay, so I guess you have got little bit philosophy of this amortized analysis. Now there are three common techniques with which we go about this amortized analysis. The one is this aggregate analysis. Another is this accounting method. Another is this accounting method, and another is this potential method. Okay? So potential method. So what we'll be doing is first we'll be dealing with this uh, aggregate analysis, and then we'll be dealing with this potential method. Accounting method will be given as an exercise to you after getting these two philosophy. Okay, you will be able to go yourself with this accounting method, right? And in most of CLRS book, wherever amortized analysis are utilized, bulk of the cases are employing this aggregate analysis and potential method. So that's why we are taking up these two, and we are leaving accounting method as an exercise, right? Okay, so the first method is this aggregate analysis. So here what we are dealing with in aggregate analysis for a sequence of n operations, we find the worst case time Tn in total. That is with that previous code fragment example we have done. Then we find this Tn by n, that is the worst case average cost, that we call the amortized cost per operation. Okay. And here the example that we'll be taking, that is given in this CLRS book, that is called the stack operations. Okay. So in our example of aggregate analysis, we will analyze stacks. However, in our stack, we will allow multi-pop operations. This has been introduced to have a nice idea of the amortized analysis. So generally the stack, what the stack does, we push and pop the elements only. We are having two famous operations, push and pop. Every computer science students are aware about that. And we do the push and pop operation on top, okay, from top. And here what we are doing is we are allowing these multi-pop operations. Multi-pop operation. Another operations we are allowing in our stack, that we are calling this multi-pop operation. That means at a time, many from the top, say if we are telling say k items, pop k items from top. Say pop, say we are having 4 items, say k equal to 2. 2 items you delete right now. So from pop, from top, this will be deleted, this will be deleted, and then this will be deleted. So this is called the multi-pop operation we are allowing, right? So our stack considers three operations. Pushes object X onto the stack S. Pop S pops the top of stack S and returns the popped object, calling calling pop on empty stack gives an error, right? So you cannot pop on empty stack. So this will be giving you the error message. And this multi-pop operation, this is k, that is what, while not stack empty and k greater than 0, pop s, and we have to decrement k by k minus 1. That means already one element we are popping, and then how many remaining elements to be popped with this k equal to k minus 1, that is being depicted here. Okay. So this multi-pop operation, one example is shown here, multi-pop operation. Say multi-pop is comma 4. Okay. So 4 elements will be popped off. So after this, it will be 5 and 2. Then if I am calling multi-pop is comma, say 6 or whatever, 5, 4, 3, then what it will be doing is it will be popping 2 elements. That's it. So that's why it is the condition is there that okay, there might be a situation that okay, the stack consisting of 2 elements and I am trying to pop 4 elements. Okay. So always we have to check whether the stack is empty or not, and also k greater than 0. So if both the condition getting satisfied, then we have to pop, right? Otherwise, whichever is not true, then we cannot do. So whenever I am popping, trying to pop 4 elements, when stack having 2 elements, then stack empty condition will be true after 2 elements being popped up, and then we have to come out of this loop, right? So that multi-pop operations we are allowing right now. So now let us analyze a sequence of n push, pop, and multi-pop operations on an initially empty stack. So initially the stack is empty, and then we are pushing, popping, multi-popping, all operations happening out here. Okay. So say first n minus 1 operations are push. So first n minus 1 operations we are having push. And then nth operation is a multi-pop. Okay, is a multi-pop. And multi-pop all these n minus 1 elements. Say I am giving that multi-pop operations, that I am invoking that multi-pop operations. So then can you tell me that what will be the time complexity of multi-pop operation only? I have pushed n minus 1 elements, and then at one go I am popping all n minus 1 elements. So what will be the time complexity of multi-pop operation only? Not n, order of n. Order of n. Okay. So multi-pop operations. So you see, now if I am analyzing for a sequence of n operation, 1, 2, 3, 4, 5, so all these operations happening, and finally the multi-pop. So for a sequence of n operations we are observing, right? And out of this one operation is taking, one operation is becoming very expensive, that is order of 1, order of n, right? That is the multi-pop. Other operations are push operations, so that will be definitely taking order of 1 time, pushing an element. So now for a sequence of n operations, if one operation is taking order of n time, and if I am taking that order of n, the worst case time complexity if I am analyzing, then one operation within that loop is taking order of n time. And how many sequence of operations happening? N number. So one operation is taking order of n at the worst case. If I am taking that operation as the representative one, then our worst case time complexity will be order of n square. Okay. So for a sequence of n operations, I have observed that one worst case operation might be order of n square. That I am taking as the representative one, and I am replacing each operation with that cost. So one operation taking order of n time, n operations will be taking order of n square time. If I am analyzing that way, that is the correct one. That is the correct one, but not the tight one. That is right one, but not the tight. Okay. Not the tight one, right? So, although this analysis is correct, but it is not tight. Using aggregate analysis, we can get a better upper bound that considers each operation of the sequence of n operations minutely. In fact, although a single multi-pop operation can be expensive, any sequence of n push, pop, and multi-pop operations on an initially empty stack can cost at most order of n. Why this is so? Because you observe we can pop each object from the stack. We can analyze that this way. We can pop each object from the stack at most once for each time we have pushed it onto the stack. So we are pushing that one object into the stack. We are pushing one object. That means that object can be popped off only once. Therefore, the number of times that pop can be called on an empty stack, including calls within multi-pop, is at most the number of push operations. Okay. So the number of push operations what we are having, including pop and multi-pop, that as pop operation is happening only once, corresponding a push, and that pop will also be consisting of this multi-pop. Okay. So this multi-pop operation can be at most the number of push operations, because we cannot invent any other pop operations. Okay, any other pop operations. Whatever push operations we are having, those many pop operations we will be having. That will be including the multi-pop operations as well. So for any value of n, any sequence of n push and multi pop operations takes a total order of n time. So what we can say is that we are having n minus 1 push operation. Then we have called in the previous example, and then we have at one go we have popped n minus 1 elements. So how many such operations we are having at most? So we are having n minus, so that will be less than equal to n minus 1 plus again multi-pop operation n minus 1, right? Or we can say that for any such sequence of n operations, we can have, so this is 2n minus 2, and that is less equal to 2n, right? So any sequence of n operations, that should be bounded by 2n, right? So that means this will be bounded by, so this will be, we can say this is equal to order of n. So that way also you can proceed, right? So now the average cost per operation will be, so this is the total cost of sequence of n operations, where multi-pop operation will also be included. And this is the total one. So the average cost will be order of n by n. So that will be order of 1, right? So this is the amortized cost per operations. So this is the amortized cost. That means worst case average cost. So in this example, all three stack operations have an amortized cost of order of 1. So that will be the conclusion here. So this aggregate analysis we have seen. Potential method we will see. Then again one more example we will see, that is called binary counter operations for both this aggregate analysis and potential method. Okay. So in the next class we will be dealing with this potential method, and one extra class I may take in this week because I have missed 2-3 classes, so that I want to cover up, right? So I can discuss with Saurabh and I can let you know. Okay. So let me, if you have any question now, you can ask.